Directed acyclic graphs, or DAGs, are very useful mathematical representations in machine learning applications. A DAG is defined as a graph with directed edges and without directed cycles. Typically, in real-world applications, edges can represent relationships between data samples, a partial ordering can represent causal ordering between data samples, and combined with transformations on nodes, DAGs can also represent the causal mechanisms which transform the values of the parent nodes in the value of the children node. In this work, we focus on DAG learning from observational data. Important examples of applications are learning of causal relationships between time events like financial orders, between biological data like proteins, or between document versions like GitHub repo. However, DAG learning from observational data is a NP-hard problem. Previous methods propose to search for DAGs which maximize some scoring functions like data likelihood. The first set of methods propose to perform discrete combinatorial optimization. Their two main downsides are that the optimization space is large and constrained and that the learning is not differentiable. Hence, these methods used heuristics to avoid too much computations and are not adapted to gradient-based optimization. A second set of methods perform continuous Lagrangian optimization. Their two main downsides are that they use costly optimization procedures and they do not guarantee valid solutions without non-differentiable processing steps since they relax the DAG constraints. To solve these issues, we make three main contributions. First, we proposed a new model for fast and differentiable DAG sampling. Second, we combine these methods with variational inference for DAG learning from observational data. And finally, we proposed an extensive evaluation of DAG learning algorithms. First, the differentiable probabilistic model over DAGs, called DP-DAG, is composed of three simple steps which can be implemented in few lines of code. We first differentiably sample a permutation matrix using Gumbel-Sinkhorn or Gumbel-Top K-tricks, which allows to specify the ordering of the nodes in the final graph. Second, we then differentiably sample an edge matrix using Gumbel-Softmax trick, which allows to sample the existence of a relationship between nodes. And third, we compute the final adjacency matrix from the permutation and the edge matrices using simple matrix multiplication. The overall procedure is expressive. Any DAG can be generated in that way. Differentiable, all steps use differentiable operations. And fast, the complexity is quadratic in the number of nodes. Then, based on DP-DAG, we proposed a new method to learn both a probabilistic model over the DAG structure and the causal mechanisms from the observational data. This model, called VI-DP-DAG, works in three simple steps. First, it differentiably samples a valid DAG adjacency matrix from a probabilistic model over DAGs. In practice, we parameterize the probabilistic model with DP-DAG. Then it independently predicts each node value by applying n different transformations on the full observation masked with the sample DAG. This allows to predict a consequence node value only based on the value of its learned causes. In practice, we parameterize the transformations with neural networks. And third, it jointly updates all parameters by maximizing at each iteration an approximation of an elbow loss with an expected likelihood term and a prior term which can be set to penalize dense DAGs. In our experiments, we consider 5 baselines using discrete combinatorial optimization and continuous Lagrangian optimization. And we use 11 datasets, including synthetic and real-world datasets with different graph types and sizes. Further, we considered a large range of tasks and show that DP-DAG can sample DAGs with more than 200 nodes in less than half a second. VI-DP-DAG always perform best or second best score to recover the ground truth DAG structure from observational data. VI-DP-DAG consistently outperforms all the baselines when predicting consequence nodes from learned cause nodes and learned causal mechanisms, thus showing the predictive power of the model. And finally, VI-DP-DAG trains from 5 times to 18 times faster than all other baselines, making DAG structure predictions more practical. We hope that you will check out the full paper Differentiable DAG Sampling. This was joint work with Simon Kibler and Stephan Günnemann from the Technical University of Munich.